Hello everyone, and welcome to the last presentation of the energy unit. Now in this case we're going to be talking about motors and engines and those kinds of things. Here's a classic 4-cycle internal combustion engine. That's what's going on inside of your car, say, for example. And when you look at an engine, it's usually not rated in its output of energy, how much energy it can transfer. Because, after all, even a small engine eventually can transfer a lot of energy. I used to drive a Geo Metro. It was a teeny little car with a 3-cylinder 1.0-liter Suzuki engine. And that little thing eventually could get up to highway speeds. Now, it took a long time to get it there. I might have had to turn the radio off and the air conditioning. But eventually I could get it up to 70 miles an hour and drive it on the highway. So it had a lot of kinetic energy. But I couldn't do that very quickly. So when we are rating a motor or an engine, we usually rate it in something that is known as power. The power output of a machine is the rate of doing work. And remember, work is a loaded term. Right? Work is transferring energy. So power is how quickly energy is transferred. So in the case of a 4-cycle internal combustion engine, you're transferring energy from the chemical potential energy of the gasoline into the kinetic energy of the car. So how quickly can your motor do that? Well, that would be important if you wanted to try to figure out which car was going to accelerate faster or which car would be better in a race. And the same kind of thing is done with electric motors. Whether you're talking about your hairdryer motor or your toaster motor or something like that, they're going to be rated in terms of their power output. Now, the equation for power comes right from the definition. It's the rate of doing work. So for constant forces, power is work over time. How much work you do in a certain amount of time. And remember, work, again, is a loaded thing. Work is an amount of energy transferred into or out of a system by means of an external force. And so our work equation, as we derived the other day, is the external force times the distance times the cosine of theta, where theta is the angle in between. So in order to figure out how much power something is outputting, you need to figure out how much energy it's transferring, how much work it's doing. Right? So that's the first step along the way. Now, units for power. Well, they come right from the equation. Power is work over time. Work, of course, is an amount of energy transferred, so it would be in joules. And time, most fundamentally, is in seconds. So we have power in joules per second. But if you were to look at that hairdryer, for example, that you have at home, it's not going to say, hey, this is a 60 joule per second hairdryer. It's going to use a derived unit. And that derived unit is named after a guy who did a lot of work on electrical engines by the name of James Watt. So 1 joule per second is defined as 1 watt of power. Okay? And it's a capital W, by the way. And I know that that's a little inconvenient because you also have a capital W in the equation, but there's only so many letters in the alphabet. It's like when we use M for meters as a unit and M for mass as a variable. W, capital W, as a unit is a joule per second, a watt. W as a variable in an equation is an amount of work. Now, watts are how many joules every second. And remember that a joule is a Newton meter. And a Newton is a kilogram meter per second squared, F equals ma. So a joule per second is a kilogram meter squared per second cubed in base units. Much easier to say watts. Now, you're probably most familiar with watts with electrical devices, like you might have a 60-watt light bulb. Well, a 60-watt light bulb is therefore transferring 60 joules of electrical energy every second into light energy. A 120-watt light bulb is transferring energy twice as quickly, 120 joules for every second, right, that goes by. So it's not transferring twice as much, it's transferring it twice as quickly. Now, very often, because a joule is not a lot of energy, a Newton meter, because a Newton is not a lot of force, remember a Newton is only 0.22 pounds, and lifted a meter is 1 joule of energy. Because that's a small unit, very typically you'll hear the metric prefixes used. Right? You might have a kilowatt. You're talking about here of power. Kilo, of course, means 1,000. So a kilowatt is 1,000 joules per second. And you might get into megawatts, which are millions of joules every second. And if you're talking about power plants, you might be into tera or gigawatts, trillions and billions, billions and trillions of joules every second. And so the metric prefixes get used here. But when you're talking about something like an internal combustion engine, like a motor on a lawnmower or something like that, or even a snowblower that we had to use a lot in the winter, you're not going to end up using watts usually. Instead, it's listed in horsepower. 1 horsepower is about 746 watts. So a 1 horsepower engine is transferring 746 joules every second. Now that literally comes from the output of a traditional typical horse. James Watt was trying to compare electrical engines to the power providers at the time, horses. So he came up with an idea of how much power a typical horse could put out. And maybe if you ran it on a treadmill or something like that, you could calculate how much energy a horse could transfer, right, when running. And so 1 horsepower is about 746 watts. It's actually a little bit over what 1 horse would do. He overestimated so that he couldn't be accused of cheating. So 1 typical horse is actually a little less than 746 watts, but that's the conversion factor that we use today. Now, one additional little way to calculate power, which sometimes comes in handy, especially with cars. Let's take a constant one-dimensional external force. Power is work over time. Work is external force times distance times the cosine of the angle in between over time. Well, if we're in one dimension, then theta, the angle in between F and D, is 0, because you must be pulling in the same direction it's moving, hence one-dimensional. And the cosine of 0 is, of course, 1. So we can plug that right in there. And we get power is, and I've regrouped these a little bit for a reason that you'll see in a moment, is force times distance over time. Now, why distance over time? Because distance over time is something that we know. What is distance over time? Meters over seconds, miles over hours. That's right, it is velocity. Constant velocity is distance over time. So we plug that in, and we get an alternate way of calculating power. Now, this is not the one that you typically use. Typically, you use work over time. Okay, but this is an alternate version if you happen to know the external force and the speed of the object. Check out the units. Force is in newtons. Speed is in meters per second. Of course, a newton meter is a joule, and a joule per second, it's a watt. So as long as we're using newtons, meters, seconds, kilograms, we're going to get joules per second or watts. So there's 2 different ways to calculate the power output of a machine. Hope you enjoy the last worksheet.